Google search is arguably the front page of the internet, and its search bar has been hammered with untrusted user input for decades. That's why I would have never thought to ever experience something like a live XSS on Google search myself. That was until I was sent the following URL. I see this weird string in the search bar coming from the Q parameter, and then I clicked into the text box. Alert 1. My colleague Masato Ginogawa has actually done it, and it's such an interesting bug as well. To understand this bug here, we need to understand some background stuff first. If you learned about the basics of reflective or stored XSS, you know that we generally advise you need to properly encode any untrusted data depending on the context where it is placed into the page. Is it placed into the DOM, inside of JavaScript, inside of an SVG, as part of a quoted attribute, and so forth. And that task alone is in general not that trivial, and we still see a lot of XSS because of that. But nowadays it is also mostly solved if you use proper web frameworks. However, we still have a huge challenge when it comes to sanitizing HTML. Sometimes web applications want to allow certain kinds of HTML tags. You want bold and italic text, but no scripts. A prime example is HTML emails displayed and rendered in a webmailer, or having a what you see is what you get editor for users to style text, but you don't want them to be able to insert active elements such as JavaScript. And what I'm telling you now will maybe sound counterintuitive. At least when I thought about this the first time, it seemed so wrong. We actually want to sanitize this in the client, in the browser, in JavaScript. But why? Should you not use some kind of HTML parser library on your server and then sanitize the untrusted data there before placing it into the web page? Unfortunately, in the use case where you want to sanitize HTML and allow certain tags but not others, you want to move the XSS prevention into JavaScript. Let me show you an example that hopefully highlights the challenge. Pause the video for a moment and try to explain how the following two HTML snippets should be understood by the browser, and how does the hierarchy look like. Especially the fact that the tag seems to be closing here, but it's also an attribute of the other tag. What does the browser do? Go pause and try it. So first of all, this is kinda invalid HTML, right? There is no HTML head or body element. But worse, the open tags miss closing tags. So what do we do now? The browser could refuse to display the website because of HTML errors, or the browser tries to be smart and fix it for you. So let's load the snippets in the browser and examine the parsed HTML, the DOM tree. The first example is a div with a script tag inside, and it actually looks kinda logical. Div opens, script tag has an attribute title and contains the string. This string happens to be a closing div tag, but doesn't matter, it's an attribute string, right? And then the browser fixed it by adding the closing script tag, then a closing div tag, and embedding the whole thing in a regular HTML document. Now look at the other example. We have a script tag which contains a div tag. But that doesn't really make sense, right? Because a script tag would contain JavaScript code, not other HTML tags. So when we look at what the browser did, we see that it took the script tag, placed it into the head, and the script source code, the JavaScript basically, is the div tag. And then we have the closing script tag. And then the quote and angle brackets are simply text after the script tag, and thus it is placed as text into the body. So both examples had a similar setup, but you experienced two weird things. First, we have the browser fixing the HTML by adding missing closing tags. And we experienced the weird parsing behavior. Because when we humans look at this, we kind of feel like it's a div tag inside of a script tag, but that doesn't make sense because the browser expects JavaScript inside of the tag. Thus, it switches the parser from an HTML parser to a JavaScript parser, and now any characters following it are interpreted as JavaScript source code, at least until we reach a closing script tag. So it's perfectly logical that the script tag ends here. So you see, browsers are very weird and it's non-trivial to parse HTML. And this behavior is actually abused in a class of XSS called mutation XSS. Some of these mutations or behaviors are included in the HTML specification and others are unique to a certain browser. And us implementing a sanitizer library for the server, trying to cover the behavior of every browser and all of the different browser versions, that makes no sense, probably impossible to maintain. That's where we come to client-side sanitation. The basic idea is we can actually use the browser's own parser to parse the string and then we can sanitize it. Clever idea, right? Now, getting the browser to parse an HTML string in a way that it doesn't execute scripts embedded in it is not that easy, but there are some techniques. Luckily, there is already an awesome and maintained JavaScript library to cover all that, called DOM Purify. It is maintained by Mario Heiderich from Cure53. Coincidentally, it's also where Masato Kinugawa works at. Let's have a quick peek into the source code to look at one example what DOM Purify might use to parse HTML. And it's right here in the file purify.js, where it creates a template tag element. What's so special about it? Let's see. I have here a browser JavaScript console, and now let me create a div element. And then I'm going to assign a string to the inner HTML. And this is basically our untrusted user input. And so I'm using here a typical XSS vector, an image tag with a non-existing image and an on-error event that executes alert. When I execute that line, we see the failed image request and the alert one popped up. The reason for that is when we do inner HTML, the browser takes a string and parses and interprets it, finds this image tag, tries to load the image and fires the on error. But let's do the same with the template element. We create it, now assign the payload to the inner HTML of it, and nothing. No alert one. But we can now take the template content and list all of the children. We see there is one child, the image tag. The browser parsed it and now it's available in the DOM for us to work with. For example, we could now make sure that the image tag has no on error attribute and we just delete it. Then we can use inner HTML again to extract the sanitized, safe HTML and use it in the real document. For example, we can now add it into the div and of course nothing happens. Very clever, right? And that's basically how DOM Purify works. But then came Masato. Masato is an incredible XSS researcher and he found a weird browser or HTML quirk, which led to an issue in DOM Purify. Let's do the template inner HTML trick again, but this time with Masato's Google XSS payload. We assign it, and now let's look at the content document tree it parsed. We have a NoScript element, and inside we have a p tag, which has a title attribute with a string. The string contains a closing NoScript tag and an image XSS vector, but it ignored it like our earlier example with the div. It is parsed as an attribute. And so now, when we sanitize this, we look at this and we determine it's safe. There's no XSS here. No JavaScript would be executed. So let's assign it to the div inner HTML. But what the F? It triggered a request to load the image and the alert one popped up. How is that possible? Let's examine the div. How does the DOM look like? What? This makes no sense. This looks totally different. Now it's like our second example with the script tag, remember? NoScript opens, then comes a bit of text, which happens to be the p title, and then it encounters a closing NoScript tag, which means the image tag after it is now a real HTML tag. It's not contained in the attribute anymore. Why did the inner HTML on the div parse the string differently than the inner HTML on the template? In our original example, we understood why the different parsing happens. The script tag just behaves differently because it contains JavaScript, while the div tag can contain other HTML tags. But this case is weird because how can the same tag be interpreted in two different ways? The answer to that lies in the official HTML specification. The NoScript element represents nothing if scripting, so JavaScript, is enabled, and represents its children if JavaScript is disabled. It is used to present different markup to the user agent, so browser that supports scripting and those that don't support scripting, by affecting how the document is parsed. And here you see how the NoScript elements should be parsed if JavaScript is disabled or if JavaScript is enabled. And our browser of course has JavaScript enabled, but it turns out that the JavaScript in the template element is disabled. So there the browser parses the given string differently. And this is exactly what happened to Google as well. Let's circle back to the Google Search XSS. I've modified the payload and added a debugger statement. This will trigger a breakpoint in the JavaScript debugger when the XSS is executed. By the way, this is a good tip when you try to debug a more complex DOM XSS to see where and why it fired. So here we are. Now we can see the call stack where we are coming from, and going a layer up, we see that the string B is assigned to the inner HTML of A. B looks already sanitized because the browser has added closing tags to it, but as you know, this is still evil, and so it triggered the XSS here. But where is the root cause? So of course, this was fixed incredibly fast by Google. Just a little bit after I got the XSS URL, the issue was fixed. But I still had the old page open. So I extracted the old vulnerable JavaScript code and the new fixed code and diffed them. Looking through the new changes, we find that here an inner HTML was replaced with an additional XML sanitizer. So we can also set the breakpoint there in the vulnerable version and have a closer look. So here we hit it, and if we scroll up a bit, we find that Google also creates a template element. This is Google's sanitizer, and it works in a similar way. Now, to provide a bit more context, this JavaScript looks a bit hard to read because of ugly variable naming. But Google's JavaScript code is actually open source, so here's Google's common JavaScript library, Closure Library. And this is the commit that fixes the issue. But it turns out it was a rollback of another change. On the 26th of September 2018, a Nintendo Switch fan made a change and removed the additional sanitizer step. I have heard that it was due to some user interface design issues they had. Anyway, that introduced the issue. So the XSS existed for roughly 5 months in the Google JavaScript library and likely affected many Google products that relied on that sanitizer. What an absolutely crazy XSS. I know, I always say that something blows my mind, but this just blows my mind.